first of all, thank you very much, and thank you very much to Bonnie and Russell to inviting me to speak here, and also very much what I'm going to be talking about, very much thanks to a number of group members in the projects today. So I've been fortunate to work with a great number of collaborators and teammates over the number of years, and of course working on schistosomes that has included our medal winner, David Rawlinson. Slightly alarming here, just as I started on schistosome work some 20 years ago at the Blair Research Institute in Zimbabwe. We see little David peeping out there, so we can see that other things change in the world over changing time, and that's David and I. So, outline. No introduction needed here, schistosomes and schistosomiasis, what I'm going to talk about. And I'm going to talk about, in terms of control, what lessons learned we have. First of all, I'll take this from what we can learn in the past from the laboratory, their potential to change, what we've learned from schistosomiasis in Asia, where I worked for a number of years, where we have very much older selective pressures, and finally what we can use this for lessons learned for schistosomiasis in Africa, where in terms of control at least, we've got quite recent, some new selective pressures being put on them. And throughout this, we're going to talk about what implications and applications this has, both for the theoretical of evolution of parasites in general, and also specifically in terms of policy and control. So, schistosomiasis. We've had plenty of our introduction here, very much disease, the intestinal and urogenital types here, 240 million people infected. And as Tatiana said earlier, is this a human? There's also very much a veterinary field to this, and schistosomiasis is a disease of profound veterinary importance too, which many people forget, with this very portly sheep here, sunken eyes again, sheep and goats, and here you can see the schistosomes themselves in the mesenteric systems of the livestock at the abattoirs, and in a disease of profound morbidity and also mortality in these livestock. As shown by Bonnie earlier, we can see there's many different species of schistosomes. The classic ones we think about are the Asian Japonicum. In Africa, we have Schistosoma mansoni intestinal, and in many ways, evolutionary younger Schistosoma hematobium here. And it's always taken that we have a sort of division between these parasites in terms of which hosts are in, and also which countries we're in, which keep them separate, host specificity. But we're living in this very dynamic, this very changing period for schistosomes. For the first time in Africa, we've got mass drug administration, where hundreds, thousands, millions of children are being exposed to the drug praziquantel for the first time. In Asia, there's also vaccination programs going for the animal schistosomes. We're also a time of global warming, changes in the environment, and one particular change we're seeing over much of the world, Africa and Asia, is this bringing in of very large dams, which of course for parasite transmitted through freshwater snails could be predicted to have large implications. The others is what we see as changes in agriculture. If you went to sort of parts of Africa 20 years ago, you'd see the animals roaming somewhat freely and people pulling them in at night. Now you'll tend to see somebody going with their livestock, predominantly against theft, and they're going into the water with the livestock, making it a prime area for exposure to both their own schistosomes, but also all the schistosomes of the animals within that same environment, and what implications and applications has. So we want to know, in this very changing environment, what potential does this have for evolutionary change in this multicellular, long-lived organism, the schistosome? So we know, and Tim Anderson touched on earlier, if you take these schistosomes into the laboratory and you put enough selective pressure on them, you can change just about anything. You can change the snail over even 2 or 3 generations in terms of the resistance or susceptibility to the snails, very strain specific, and also the mating potential, whether they want to mate as male or female, depending on the infection status and resistant status of the other snails. If you take the parasite, again, within 2 or 3 generations, if the selective pressure is strong enough, you can change its infectivity, its virulence, avirulence, reproductive rate, mating potential, and most importantly, in terms of control, you can select for the drug resistance, praziquantel resistance in the laboratory. And it's a very dynamic situation where you've got ongoing co-evolution between the host and the parasite all the time. But that's in the lab. What happens if you take this out to the field? First of all, lessons learned from Schistosoma japonicum in Asia. China, in particular, has had magnificent control efforts for over 50 years. They've put the drugs of prosequantal, health education, mollusciciding, environmental modification, and behavioral change. They've put everything at this parasite. And it's actually remained endemic in 7 out of the 12 provinces and actually re-emerged in some areas that were previously cleared. And the main reason to suspect for this is that Schistosoma japonicum is classed as the only real human schistosome which is a zoonotic transmission, where you've got transmission between animals and humans. And indeed, through a range of epidemiological, molecular, mathematical modeling programs, we've shown that if schistosomiasis in China was purely a human schistosome, the control procedures they put at it are sufficient to eliminate this disease. But it's actually remaining in these animal populations and reinfecting the humans. It's predominant in the lowland areas are these bovines, but showing how dynamic and sophisticated this parasite is, where you remove the bovines, or up in the highlands where you don't tend to find bovines, the Schistosome japonicum is actually transmitting through the rodents. And just as Tim Anderson was talking about with Mansoni, we see very dynamic changes in both genetics, but also in the chronobiology of this parasite. So up in the highlands, you find japonicum actually shedding from the snails at night for this nocturnal crepuscular organism, whereas down in the lowlands, shedding during the daytime for the humans. So we can see that if we've got a zoonotic reservoir, we've got the challenges to achieve elimination of this major parasitic organism. So what lessons can be learned for Africa from Mansoni, the causative agent of intestinal, and Hematobium, the causative agent of urogenital schistosomiasis? So the first question, when most people start in Africa, when we're working with SCI, with allanfenic here, and putting very large drug pressures on the parasite, what's the potential for drug resistance to emerge? May need to be updated now. Between 2003 and 2016, when I was at SCI, over 140 million prosequantal treatments were given to children, massive drug pressure selected for the first time. But it's been very successful, and particularly in reducing morbidity of this parasite, so much so that the World Health Organization have revised their strategic plan for this very ambitious vision of a world free of schistosomiasis, and particularly to control morbidity due to schistosomiasis, but to eliminate schistosomiasis and interrupt schistosomiasis in endemic member states and selected African countries by 2025. So these very big, ambitious aims through control. Pharmaceutical companies, Merck KGaA, we are committed to continuing our efforts in Africa in cooperation with WHO until schistosomiasis is eliminated. And they, from 2016, their donations of prosequantal for this control jumped from 25 million a year to 250 million prosequantal tablets a year. So again, this massive new selective pressure on the parasite. So the questions, when we start, we say, will drug resistance develop or not? Lots of examples say, don't worry about it. It hasn't happened in China. It has happened in Egypt, where the first control measures were done, but there seems to be very high cost of resistance, so after 10 years it hasn't spread or hasn't established. We always predict this very large refugia, and this is a population that is not going to be treated by the drugs. Even with the best control programs, we're not going to get that drug out to everybody. So whoever the parasites are going through, where there's no drug pressure, we have this refugia, which is very good at preventing resistance developing. And the other thing is, of course, we've got this long generation time, about 7 years of the average age of a schistosome worm. There was some chap in Britain not very long ago who had been not in Africa for 40 years and was still shedding eggs. So it can be a very, very long-lived parasite. But there's also lots of reasons to predict that schistosomiasis resistant prosequantal could develop. We know we've got resistance to all the veterinary antihelminthics already. We know we can select for it in the laboratory and in animal models, and often over very short periods of time. And we know that these MDA programs are highly successful and very large pressures put on the parasite. The other big problem, we are reliant on one drug. We have prosequantal, and that's the only drug we've got in use for treating schistosomiasis. It's a great drug, but we don't even really know how it works. And also monitoring is difficult. We have insensitive parasitological measures, particularly when we get down to the low infection intensities. So the question could be, could we have these rare resistance-conferring alleles already present in untreated populations? So this, as Bonnie introduced, the beauty of bringing in molecular biology and population genetics in particular here. This is in Tanzania. We can, by going into the children and taking the parasites, the Miracidia that hatch from their stool, you can go and you get a profile for that child. You can go back after 6 months and a year, and you can find that child still infected, but it's infected with a different genotype. So we're seeing reinfection, not treatment failure. And likewise, if you look at the profiles of the population over time, you can see change, but this hasn't been selected with resistance in Tanzania. However, if we looked in Uganda, right from the start of these programs, we first started SEI, if you go into some children, we had some children where we'd give that prosequantal to, you know the child had taken prosequantal, you go back 6 weeks, 6 months later, and that child is still infected, and it's still infected with the same genotype. So this is a treatment failure. It's not one clear treatment failure, it's a variation throughout the population, the natural standing population on which selection can act. And likewise, if you look at the population genetic structures, we can see very clear differences in the Ugandan population shifting over time in line with the drug pressure imposed upon them. Here, work with a PhD student, Tom Crellin, and also Martin Walker. Here, now at the RBC, looked at using general linear model to look at the egg reduction rate of these parasites from children in Uganda, depending on whether they come from a population with low past drug history, few numbers of prosequantal treatments, a medium number of prosequantal treatments, or if they'd had 8, 9, 10 prosequantal treatments in the past. And you can see that these populations where they had very high MDA pressure, we are seeing a significant number of children with the egg reduction rate going down below that sort of gold standard of 90% clearance. This is the same data shown in a different way. This is the group of kids at the egg reduction rate if they're under medium or low past pressure, selective pressure, and we're seeing this shift down in the children from populations that have had a very high number of past prosequantal treatments. So we are seeing potential evidence of change in association with the drug pressure imposed on them. The next stage was to take genome sequencing and to look at what impact the parasite pressure is having on the genome of this population using new detection methods again with Tom Crellin, a PhD student. And it's quite early days yet, but took parasites from these children in Uganda, both pre-prosequantal and post-prosequantal, and on the pre-prosequantal ones and the clearers, and screened the genome to look at any areas of under high selection in association with whether they cleared or they didn't clear. Again, very early data so far, but you can find SNPs in a region which was highly correlated with the drug response. And the interesting thing that the SNPs predicted in the region of calcium channels. And as I said, we don't really know the mechanism of action of prosequantal, but we know it's something to do with the calcium channels. So this is an area of high interest, which they're following up through RNAi analysis with Sanger. So, schistosome prosequantal resistance. We have some potential for change, but of course the big other question are resistant conferring alleles the only parasite strategy involved in any apparent treatment failures found? And then he will go on to schistosoma hematobium in Africa, the causative agent of urogenital schistosomiasis. And this is important because in contrast to the japonicum that I started with, which is taken as a zoonosis, schistosoma hematobium was always taken as a uniquely human schistosome. So you would think for control pressures, for MDA programs, this would be a good parasite to target for elimination if we can hit the human population hard enough alone. So we take one country, Niger, for example, one of the countries, Niger, which is targeted for local interruption of transmission. And this is SEI data, and you can see that actually the great impact of the MDA going on, and that this is the level of the mean intensity, and you can see it goes right down over time, but there's very large confidence intervals, very large variance in the populations, where some areas going down and some areas are remaining rather high. And you look at the SEI sentinel sites over time, and you can see that despite clear high coverage, known reported high coverage in these areas, some populations, notably here Kakuru and Tabalat, are maintaining very high levels Here, 80, 90, 95% infection prevalence, often very high infection intensities after 5, 6, 7 years of very high coverage and successful MDA. So what's going on? First question when we saw this is that have we got resistance going on? So with Amadou Garba leading the program, took a random sample of these children, followed them over time and gave them prosaquantel, and indeed the drug works very well. It clears them out. But what you find is this very, very rapid bounce back. And the bounce back became more interesting is when we'd see this bounce back. We'd see this bounce back by 6 weeks after the initial prosaquantel treatment. And this is important because hematobium takes 8 weeks to reach maturity and start laying eggs. And we were seeing this apparent urogenital schistosomiasis bouncing back to very high infection intensities by 6 weeks, which is the average time for the intestinal schistosomes to reach maturity and start laying eggs. So, what's happening? So this has nicely been beautifully introduced by Louis Albert, by Bonny, by Ferris. What's going on is a different life cycles and what we think about of schistosomes. You have the male and female. The conventional wisdom is that they mated with their own kind and they lived happily ever after forever. But that's not so true, that we do see mate swapping and mate mixing, particularly as we saw in the laboratory, under pressures of very high selective pressure, such as going through a resistant snail or high drug pressure. It gets even more complicated is that these schistosomes don't really mind mating either with their own species. They'll also quite happily mate with a different species. And for example, here we see the schistosoma mansoni, the causative agent of intestinal schistosoma, will quite happily mate with schistosoma hematobium. The reason I've got a mule here, it doesn't cause mule, is because this is a classic. They mate, they're very phylogenetically apart, and you tend to get infertile hybrids like the mule when the horse and the donkey. However, if these parasites are quite closely related here, hence why we get a baby, then actually you cause fertile hybrids. So here, for example, the livestock, Curasoni and Bovis, if they pair, you'll get fertile hybrids that can go on to infect the next generation. Gets even more exciting is when you get an animal schistosome, Curasoni or Bovis, pairing with the human hematobium, and they're also fertile and produce the next stages to increase an ongoing transmission. So here, what we wanted to find out, and the study that Bonny briefly mentioned, is that we want to look at areas of high anthropogenic change where we're seeing changes in mass drug administration, changes in animal husbandry, impact upon the environment and the time of the Anthropocene, and what impact does this have on the coming together of schistosomes and particularly interspecific schistosome interactions. And where we predict these areas of high transmission, high anthropogenic change to have impact on the transmission potential, the morbidity, and the drug efficacy. So what we want to know is the causes and consequences of these zoonotic hybrids, where we're seeing the animal and the human schistosome come together. And particularly where, why, and what next. Because again, we don't know if these schistosomes hybrids have been around forever. People have been studying them, as Vaughan will have studied them many years ago. They've been studying them for years and suspected them for years. So it may simply we're getting better molecular tools and we're picking them up. Or are they changing in response to high anthropogenic change? And many have been found across many parts of Africa. So what we're doing is we're going into 2 sites or 2 regions within 2 parts of West Africa, Niger and Senegal, and doing very, very detailed studies to look at, for the first time, the real transmission dynamics of these zoonotic hybrids and to see the potential of change. So over 3 years going in to account for difference in transmission, time of year, going 4 times a year, we're of course looking at the snails, what's going on in each of these sites, snail surveys. We're then looking in very much detail at the animals, throughout the animals, full postmortems, intestinal, bladder, urine. You'll see me here with my hand up a dead cow's bottom. That's the joys of fieldwork. And we're looking at the transmission dynamics over time. not just the abattoirs. Here, two of the PhD students, Stefano and Anna, have their hand up a living animal's bottom to get the stool, and we also collect the urine. And here you see Elsa's novel use of a selfie stick to collect urine from often very angry cattle, so we can look at the urine, see what profiles we get. Also, again, not just livestock, we're looking at the wildlife, local wildlife, to see, as we saw, that was a key role within the Asian, the Chinese schistosomes. Could they be playing a key role within the West African too? So looking at these in the countries, particularly in Senegal, over the 3 years. And of course, studying the children and the adults across the full distribution repeatedly. So with that, we had to, in many ways, start at the beginning. We have quite good methods of parasitology in the humans. When it comes to the livestock and different livestock, in many ways, we had to go back to standards, to optimization, make new gold standards, and looking at a range of diagnostic measures, both standard and new ones, such as the CCA and the CAA here. Preliminary results, if you can say, for Niger, we have a slight problem. This is a government UK map of where we can go and where we can't go in Niger. And as you see, our sites are in current high terrorist no-go zones. So that makes a little bit of a challenge to field work. But never mind, we've got very good partners there, and field work carried on. And we can see, we'll go into more detail in the animals in Senegal, but we get a good combination of the Curaçao, the Bovis, and the Curaçao and Bovis together. The children we can see in these areas, transmission is still really high. We have like 64% to 71% of the children infected and 13 to 45% of the adults infected. And again, with a combination of hematobium with Curaçao, and hematobium with Bovis, these hybrids. And we'll come back to further detail on this in a moment. And all shedding from the snails too. In fact, there's a whole plethora of parasite combinations. These really don't mind who they mate with. We've got male, females with different species, all mating, but all within the same combinations within, this is coming out of the children and the adults within Niger. So we get this whole successful interbreeding between parasites, which of course raises the concept of what is a species per se, because these are viable offspring in every combination we look at. However, schistosomiasis is a focal disease, and we find this is a heat map, and we find very differences in the profiles between the sites. This is Tabalak. This is just different profiles of different combinations of the hybrids we see. And actually in Tabalak, though we can't see most of them are actually hematobium with hematobium. Most of the schistosomiasis and urogenital in Tabalak is actually pure hematobium, but you go to Kokoro, the vast majority is actually Bovis with hematobium zoonotic hybrids. And why? If we look at the habitat, they're both sites close to fixed water bodies, but actually Kokoro is close to the Diama Dam, which is a new dam being brought in, area of high anthropogenic change. So can we propose that actually this very high proportion of zoonotic hybrids could relate to this anthropogenic change going on? If we look at Senegal, we've looked in huge detail at the animals. Again, you can see we're looking at abattoirs and living cattle. Here we're developing sensitivity analysis and pseudo-gold standards for the different measures to detect schistosomiasis in animals. And you can find, consistent with the social studies that another PhD student, Louise, is looking at, you've quite different profiles in the animals in the abattoirs and in the living livestock. And this is consistent with which animals are putting into the abattoirs. But you can see, again, very high levels of infection, differences between the sites, for example, 64%, 79% in cattle here, but then quite different in some of the sheep, but still high levels, both the sheep and the goats. Also, wildlife, interesting. Here we get these combinations again, and here where it gets very exciting, as Vaughan raised, this is where we find hematobium hybrids within the rodents too, for the first time. The children, again, they're very high levels of infection, and again, big combinations of hybrid combinations, very high level of zoonotic transmission, and very high levels of zoonosis coming out from the infected snails in the population. So what we want to do next is we want to expand upon the transmission models, the different levels of R0 by key hosts that we developed in China with Japonicum, and look at which are the most important hosts for continuing this transmission cycle to the humans. And it gets even more exciting with hybridization going on in West Africa over and above that with just Japonicum, as we have to bring in where these hybrids are happening and which are the most key important hosts. So the first models are just beginning to come out now in terms of transmission dynamics. So what else are we looking at? Different pathology, morbidity by the different single species, by the host profiles. We know in humans it's a very different morbidity profile if we have a mixed infection with Mansoni and hematobium, but what are the different profiles in the hybrids versus non-hybrids? So again, we're using a whole range of classic and novel techniques for morbidity. We want to look at drug efficacy. As I said, from the early studies in Niger, the drugs are working very well on these hybrids. And one reason for this could be, in fact, like China, we have this very large animal refugia, where you could say that a large number of the animals aren't being treated for the drugs, so we're not going to have much risk of drug treatment, drug failures developing. However, as ever, it gets far more complicated when you actually go down to the ground and find uses and misuses of praziquantel in animal schistosomiasis. These farmers, these veterinarians know their animals have schistosomiasis and they are treating them. They are treating them with whatever they can get. They're treating them with the only praziquantel they can get in the country, which is Atenicure with levanosol, which is just stated at the dose for tapeworm. Unsurprisingly, they're saying it doesn't work. What the most of them are doing is actually they're buying at the markets the praziquantel donated by Merck for free use for the children are turning up in the markets and the veterinarians. And though they're quite open that they don't know about the dose, they haven't got availability, but we have this high demand to treat the animals, so now we have to work in how do we help manage, particularly when we start bringing in the potential role of animal schistosomiasis and resistance developing. Viable hybrids. Have we got increased transmission potential? It gets, again, as Vaughan raised, it gets quite exciting here, as you can see in the livestock. Curasoni and Bovis hybridize, but also we find within children, Niger are infected with these Curasoni and Bovis. And these are animal schistosomes which on their own, there was no evidence they could actually infect humans, but actually as a viable hybrid, they can then infect humans, and we're finding a number of these cases. The other, as Bonnie introduced, of course, the nice German tourist. It gets all very exciting for schistosomiasis, where German tourists and French tourists go on holiday in Corsica and come back weeing blood, and they've got urogenital schistosomiasis, and that is this, again, Bovis with hematobium hybrid. And again, the potential for hybrid vigor, ongoing transmission in the hybrids relative to the single species. So the implications and applications, lessons to be learned. Schistosoma and Mansoni. We are seeing potential evidence of reduced drug efficacy, at least in some areas where we've got the highest MDA pressure, and what implications will this have for ongoing transmission. Lessons to be learned in terms of hematobium in Africa is that hematobium can quite clearly also be a zoonotic parasite, and the implications of animals, both for the cost and the health of the animals themselves, but also from the human-centric focus in terms of we target for elimination if we have a zoonotic reservoir. All this should be working with WHO to bring in policy change, because it goes back to the original elimination targets. And again, when David Molyneux was saying about if we ignore the vectors, we're not going to achieve elimination. If we ignore the animal hosts in Africa too, we're unlikely to ever achieve elimination. And again, from the One Health perspective, it just shows again the clinicians working with the veterinarians, working with this different environment, how only together can it help improve animal and human health of this both very ancient and emerging infectious disease. And thank you very much once again.